Hi everyone, I'm Haifeng. I'll talk about algorithmic persuasion with no externalities. This is a joint work with Shaddin at USC. What is persuasion? Well, let me start with an example that many of you are familiar with, writing recommendation letters. So to be concrete, let's say there is an academic advisor. He needs to write a recommendation letter for his students to apply for 2 fellowship programs. For example, these 2 fellowship programs. So from the past many years, it's publicly known that these advisor students, 1/3 of them are excellent and 2/3 of them are average. So this fresh graduate is drawn from this population uniformly at random. So he's going to be excellent with probability 1/3. Now, these 2 fellowship programs, they have identical payoff structures. In particular, they're going to get a utility slightly above 1 if they award an excellent student, but they're going to get a utility -1 if they award an average student. If they do not give out the award, then they get utility 0. So you can see that they would only be willing to give out the award if the probability of the student to be excellent is at least half. But a priori, this fellowship program, they do not know whether the student is excellent or not. Now, so here we assume that the student can accept both offers. Now, on the other hand, the advisor, he's going to get utility 1 if the student receives at least 1 fellowship, and he gets utility 0 otherwise. In other words, he only cares about whether his student get a fellowship or not. But the advisor has an informational advantage. Namely, he knows precisely every student is excellent or not. Well, since the advisor takes students every year, he somehow needs to determine a long-term policy about how to write recommendation letters for his students. Well, so the question then is, what is his optimal policy for writing letters? Well, his first attempt is try to reveal no information, and this is also equivalent to always say your student is excellent, because that doesn't reveal anything specific about the student. And you can see that in this case, unfortunately, the advisor is going to lose credibility, so that the fellowship program basically just behave according to their prior belief about these students. And in this case, because the student is less likely to be excellent, so no student will get the fellowship. And the advisor gets utility 0. Well, his second attempt is try to reveal 4 information, and that is just be honest about the status of the student. Well, in this case, 1/3 of the students are excellent, so they will get the fellowship. The advisor also gets utility 1/3. The question then is, can the advisor do something better than 1/3? Well, it turns out that he can, and the idea, as some of you might already know, is to reveal noisy information. In particular, the following signaling scheme, the following scheme going to give the advisor utility 2/3. That is, whenever the student is excellent, you're going to send a strong letter to both fellowship programs. But when the student is average, half of the time you also send a strong letter to both fellowship programs, and half of the time you're going to send an average letter. Now, from the fellowship program's perspective, if they receive a strong letter, they know that this student is not excellent for sure, but it's easy to see from the probability flow that they're going to infer the student is excellent with probability half. So they will still be willing to give out the fellowship. But when they receive an average letter, they know for sure that the student is average. So in this case, you can see that the advisor kind of doubles his utility from the previous one. The question now is this the best the advisor can do? Well, it turns out that the advisor can actually further improve upon this utility. If you recall all the 3 schemes I have described, they have a common property. That is, they're going to always reveal the same information to both fellowship. For example, here, it's always sending a strong letter to both fellowship program, or always send a weak average letter to both fellowship programs. This is called a public scheme because basically you're revealing the same thing to both fellowship programs. You could have just send a public scheme, for example, like you put your recommendation letter on your homepage. That's actually that's the same thing because everyone receives the same information. Well, if the advisor is allowed to communicate privately with different fellowship programs, which is indeed the case when you're writing letters, because you send the letter to different program. And it turns out, in this case, he can improve his utility actually to 1. So the scheme is as follows. Whenever the student is excellent, you're going to send a strong letter to both fellowship program. But when the student is average, you're going to send a strong letter to 1 fellowship program that is chosen uniformly at random. It's easy to see that in this case, conditional on a strong letter, the student would still be excellent with the probability half. But the trick here is that the advisor tried to anti-correlate the case of sending the strong letter, so that there is always at least 1 fellowship being recommended the strong letter. So in this case, the advisor gets utility 1. So if you're curious about what is the gap between like optimal private scheme and optimal public scheme, it turns out that slightly generalize this example to n fellowship programs, you can show that the advisor's utility of optimal private scheme can be at least n plus 1 divided by 2 times the optimal utility in the public scheme. So you can see that it's actually a big advantage to use a private scheme. So far, I have shown you an example where how the advisor can make use of his informational advantage to influence the fellowship program to take actions that the advisor prefer. And more generally, persuasion is the act of exploiting an informational advantage in order to affect the decisions of others. And this is intrinsic in most human activities and have many applications. For example, this ride-sharing system just talked in the first talk. And in fact, if you think about the presentation here right now, I'm also doing a persuasion game. So unsurprisingly, this has been the theme of a large body of recent work. So most related to ours is the following 2 models. The first is a Bayesian persuasion model proposed by Kamenitsa and Jensko, who study how to persuade a single decision maker. And however, in this paper, we focus on a recent model proposed by Ariely and Barbichenko, who study how to persuade multiple decision makers, but with no externalities and binary receiver actions, which I'm going to now define formally. So here, there's 1 persuader who we're going to call sender, and the multiple decision makers who will be called receivers. So in the previous example, the advisor is the sender, and each fellowship program is a receiver. Each receiver is going to take a binary action, AI, and result in the receiver utility that depends on his action and the random state of nature theta. In the previous example, AI is basically to give the fellowship or not, and theta is basically the student is excellent or not. So here we made the no externality assumption. That is the reward, the utility for receiver I does not depend on the other receiver's action. So it only depends on his own action. That's no externality assumption. On the other hand, the sender's utility is a set function, f, that depends on the set of receivers who are going to take action 1. So in the previous example, this function is basically the minimum between cardinality of S and 1, because the advisor would be happy if the student gets at least 1 fellowship. And here we're going to assume that f is non-negative and monotone non-decreasing. So action 1 is preferred by the sender. So the receiver basically only knows the prior distribution about this random state theta, but the sender observed the realization of theta, which is precisely like the previous setting. We assume that the sender can commit to a signaling scheme, which is a randomized map from the set of states to the set of signals. In the previous example, it's basically a randomized map from the student of the states to a recommendation letter. And this can be randomized because you see, like when a student is average, the advisor sometimes write a strong letter, sometimes write an average letter. Here we will look at 2 natural signaling schemes. One is a private scheme where you can send different signal to different receivers. Another is a public scheme where you are constrained to send a public signal to everyone. Okay? And each receiver, they're going to receive a signal and does a base updates about the state of nature and then base response. For example, each fellowship, they're going to receive a recommendation letter. They're going to update their belief about the student and decide to give the fellowship or not. The main contribution of this paper is we pin down the computational complexity for optimal public and private persuasion for natural classes of the sender's utility function, which recall is a set function. So just as a side note, the work of Arely and Barbichenko, they focus on explicitly characterizing the optimal private scheme when there are only two states of nature. But here, we look for algorithms that work for any states of nature. So now I'm going to go ahead and describe our results and techniques. So we start from private persuasion, and we first establish a polynomial time equivalence between private persuasion and optimization. In particular, we show that the exact optimal private persuasion can be computed in polynomial time if and only if the optimization the unconstrained optimization problem of maximizing the sender's utility function plus an arbitrary set function of S can be solved in polynomial time. Okay, so to prove the theorem, we started with a simple observation. That is, we claim that that is the optimal private scheme going to only need two signals for every receiver, which going to recommend action 0 and 1 as his best response, respectively. This follows a simple revelation principle type argument. Imagine that you have a strong ladder version 1 and a strong ladder version 2, but if they result in the same outcome, so you could have just written one strong ladder version. Using this observation, then you can write this. You can solve the private persuasion problem by an exponentially large linear program, where the only variable pi theta s is the probability of recommending action 1 to receivers in set S, conditional on the state of nature theta. You don't have to look at the LP in detail. I'm actually writing in an abstract way, but the objective is simply the sender expected utility. And the first constraint is basically saying that whenever the action 1 or 0 is recommended, it should have to be your best response. We call this persuasiveness constraint, which is pretty much just like it sounds like. So the last two constraints basically saying that the scheme should be a signaling scheme. This linear program is exponentially large because there were exponentially many variables. In particular, this pi theta s, this s belongs to the power set of all the receivers. But crucially, this LP has polynomially many constraints. So its dual has polynomially many variables. To prove this theorem, one direction is relatively easy. If you just want to compute the optimal private scheme, you can just solve the dual of the previous linear program. And it turns out that this optimization problem can be used to construct a separation oracle for the dual problem. The other direction is more intricate, which involves constructing a persuasion instance to encode this function maximization problem. But I'm not going to describe the details here. As a simple corollary, this infers that when the sender utility function f is supramodular or anonymous, you can solve the problem efficiently. The anonymous here means basically the function only depends on the cardinality of S. So when it's supramodular, it's because fs plus a modular function then is also a supramodular, and the maximizing a supramodular function is tractable. And when it's anonymous, there is a very simple algorithm to solve the optimization problem. And this actually algorithmically recovers and unifies the results from Arely and Barbichenko, and some results from the recent work by Barbichenko and Barman. Also generalized their result from two states of nature to many states of nature. But in this theorem, everything is about exact optimization and exact optimal private persuasion. I think an interesting question is to study whether there is some approximate version of hold for this theorem. We don't know the answer, but we know that in one of the most natural case, this holds actually. So that is when the sender's utility function is monotone submodular. In this case, we show that a private scheme that achieves sender utility at least 1 minus 1 over E opt minus epsilon can be implemented in polynomial time. The proof of this theorem can be divided into two steps. In the first step, we establish a structural lemma about the optimal solution of the previous linear program. If you recall, the variable in the linear program before is pi theta s. And for every theta, this pi theta S for different S is actually a distribution over the power sets of receivers, which I'm gonna, for convenience, I'm gonna denote it as pi theta. Our structural lemma says that the previous linear program admits an epsilon optimal solution such that for every the pi theta is k uniform for every theta, where for a polynomial k, where k uniform basically means it's a uniform mixture over k subsets. This is proved by a probabilistic method. I'm not going to mention detail here. The second step is then to approximately compute such a k uniform private persuasion scheme. So how to do this? Well, if you think about it, it's basically you're going to pick k sets for every theta, so that you maximize the sender utility, except that you're going to normalize the utility from each set by its probability 1 over k. And it turns out that this is essentially a monotone submodular function maximization subject to metroid constraints. And it's well known that there's a 1 minus 1 over approximation for this problem. Combining these two steps, you get a proof for this theorem. So as a remark, it's shown before that it's actually NP hard to obtain an approximation ratio better than 1 minus 1 over E, even when there were only two states of nature. So this shows that our result is pretty much the best you can hope. Okay? So far I have been talking about private persuasion. So one natural question to ask then is, what if you are constrained to send a public signal? The computational result for public signaling turns out to be a sharp contrast and is very negative. In particular, we show that it's actually NP hard to approximate the optimal public scheme to within any constant factor, even when the sender's utility function is simply the cardinality function. And we also show that there's no additive pitas for this problem. I'm not going to show the proof here, but roughly the intuition here is that the persuasiveness constraint for public persuasion is much more difficult to express than that in a private persuasion case. The reason is in the public signaling setting, one signal is going to result in an outcome which is basically a profile of receiver actions. But there were exponentially many profiles. The persuasiveness constraint have to express this like for every outcome. So there were exponentially many constraints. But in the private persuasion setting, the persuasiveness is basically for every receiver, which is kind of decorrelated in the private persuasion case. That's what makes the private persuasion more tractable. This brings me to the conclusion of this talk. Basically, I told you the private persuasion and the public persuasion. Private one is usually tractable and effective. The public one is usually intractable and ineffective. For follow-up questions, as I mentioned before, it's interesting to look at an approximate version between optimal private persuasion and optimization. Going beyond the model, I think it's interesting to look at the setting where there were externalities. That is, the receiver's action might affect each other. For example, in the routing game setting or like in anonymous game setting. And also, it's interesting to, so I'm assuming here, doing the whole model, that the receivers will not share their signals with each other. It would be interesting to see what if the receivers can kind of share their signal with some of the other receivers. How would the problem become? And that's it. Thank you.